Class 12 Relations and Functions. Exercise 1.1. First question in that fourth sub-question. Determine whether the given relations are reflexive, symmetric, transitive. So how the relation is defined here? Relation are in the set Z of all integers defined as R is equals to xy such that x minus y is an integer. Okay, so let us solve this. The solution is here. Z is equals to 0 plus or minus 1 plus or minus 2 plus or minus 3 and so on. So we know that the given set on which the relation is defined is an infinite set. Now how the relation R is given here? R is equals to xy such that x minus y is an integer. They have given this relation in set builder form. So we don't know what are the elements directly, they have not given, and we can also calculate it, but you will be having infinite elements or infinite ordered pairs. So we'll just keep this in the set builder form. Okay, so first before going to the sum, let us understand the property here. How does it work? I have taken z, that set of integers from 0 plus or minus 1 plus or minus 2 plus or minus 3 and so on. Here relation, we will write this in the roster form, that is we'll write all the elements that we are going to get. Okay, so here the property is defined as x minus y is an integer. This is the main important thing here, like this is the boss, like this will define what elements I am supposed to write here. So x minus y is an integer. So let us take any integer. Example, let us take 0 and 2. So 0 minus 2, and this is also an integer, right? So therefore 0 comma minus 2 belongs to the relation. Okay, so if this property is satisfied, I can write this pair here. Okay, let us take one more example, 3 and minus 9. Okay, so 3 minus of minus 9, that is 3 plus 9, which is 12. 12 is also an integer, it also belongs to this set of Z. So we can write 3 minus 9, that is 3 comma minus 9, this ordered pair here. 3 comma minus 9. So to write any ordered pair in this relation, we have to take the permission of x minus y as an integer, correct? Exactly, right? Suppose if I randomly select some ordered pair AB. So if AB is already there in R, then we know that A minus B must be an integer. If already you are taking an ordered pair from here, then obviously this should satisfy this property, A minus B is an integer, right? Suppose if I take some random integer M and N. So if it is already there in the relation, then it can exist here only with the permission of this property. That means M minus N must be an integer, right? So this is the hidden thing here. If there has to be an ordered pair in this relation, then it must satisfy this property. If it is satisfying this property, then that corresponding ordered pair will be here. Okay, so with this intuitive understanding, let us solve the sum here. Okay, so what is a reflexive relation? How do we define it? If A comma A belongs to R for all A belongs to, what is the given set here? Integers, right? Now here let us check if R is reflexive. So how to check if it is reflexive? Let us take let A belongs to a set of integers. So we know that A minus A, if we take the same number A minus A and subtract with it, we know we are going to get 0, and 0 is an integer. So this implies A minus A is also an integer, right? So if a minus a is also an integer, is it satisfying this property? A minus a is also an integer. That means it got the permission here to exist in this relation. So we can clearly say that a comma a belongs to R for all a belonging to Z. So therefore we can conclude that R is reflexive. Clear? So the property is satisfied, then this ordered pair will be in the relation. Okay. Now this is really interesting. So now to say that the relation is symmetric, what is the condition? If A, B belongs to R, this implies B, A also belongs to R for all A, B belongs to this set of integers. Okay. So here already one is taken from this, one ordered pair will be selected from this. We have to see whether it is symmetric by inverting it. If it is inverted, the same ordered pair belongs to this set or not, we have to check. So they have given if AB belongs to R. So if AB belongs to R, that means it has to satisfy this property, that is A minus B is an integer, right? A minus B is an integer. Now if A minus B is an integer, we have to use one more property here, that is we want the answer that B minus A is also an integer. B minus A is also an integer. So therefore B comma A belongs to R. So this is what we want to prove. Now if you observe one thing here we have A minus B, we can take this for granted, but we have to prove that B minus A is an integer. So if you observe this one, what we can do here is, if we just subtract this A minus B, minus of A minus B, we will get minus A plus B, which is nothing but B minus A, right? So this clearly shows that B minus A is also an integer. So B comma A belongs to R. Okay, so let us just once again go through it, right? Suppose if I have A and B here, so A minus B is also an integer. That means A comma B belongs to this set, right? A comma B belongs to this set. We'll take one example, 4 and 7. So 4 minus 7, we are going to get minus 3, right? Now what is the, how do you invert this minus 3 now? Minus of minus 3, which is equals to 3. Now 3 also is an integer, right? So that means if you just reverse this one, that is 7 minus 4, even 7 minus 4 is also an integer. 7 minus 4 is also an integer. So if this is an integer, then 7 comma 4 belongs to this set. Okay, so we considered 4 7, but we proved that even 7 4 also belongs to this relation. Clear? So next we will prove transitive. So how do we prove transitive? If AB belongs to R and BC belongs to R, then AC belongs to R. So here two ordered pairs can be selected. So if AB belongs to R, that means I am taking one ordered pair from this. If I am taking an ordered pair from this, it is satisfying this property. Implies A minus B is an integer, right? Now, and we are taking one more element, that is BC belonging to R. So we are taking one more BC from here. So what does this implies? B minus C is an integer. B minus C is an integer. So what we have to prove, that we have to prove A minus C is also an integer. A minus C is also an integer, and we have to prove that AC belongs to R. So this is available to us and we have to reach here. So A minus B, B minus C is available. We have to reach A minus C. So if you observe here, we need to cancel this minus B and plus B, right? So can we cancel it directly? We can cancel it along with the property. We must be aware of this property that sum of two integer is also an integer. Sum of two integer is also an integer. So now you have the permission to add. So a minus b plus b minus c. Now what we know here, so this implies, so we can cancel this minus b and plus b. We got a minus b, a minus c. And this property says that sum of two integer is also an integer. So it is saying that a minus c is also an integer, which is what we wanted, right? And we proved that AC belongs to R. So what we can conclude here is R is transitive. Okay. Now what is the final conclusion? The given relation R is equals to the set of ordered pairs such that x minus y is an integer is reflexive, symmetric and transitive. Okay. The whole idea behind solving this here is they have given the relation and the property. If the property is satisfied, that element will be present here. If you're taking this element from here, then already the property is satisfied. Okay.